In this lecture, we will discuss an example for the controllable canonical decomposition and hence the stabilizability for such a linear time invariant system. So, consider this example where this is the linear time invariant system that we have in hand. A, B, C matrix are given, the D matrix is 0, which means the output does not have explicit relationship with respect to the input. It depends on the input to the state vector, and the system is a real system. The question that we ask here is the system controllable? So to answer this, we found the controllability matrix using the A and B matrices as one, and we have to see whether rank of QC is 3 in this case or not. This so turns out that the rank of QC is checked will be 2, and that is going to be that is less than 3, of course. So the system is not controllable. Now the rank of QC indicates that there are two number of linearly independent column vectors. Okay, or two number of linearly independent columns in this particular controllability matrix. So what we will do here is we will construct a state vector such that the first two vectors, the first two states of the state vector would be controllable states, and the last state or the third state of the state vector would be the uncontrollable state. Okay. You note that the rank of QC essentially tells you how many controllable states are there and how many uncontrollable states are there. Okay, so whatever is the rank of QC, that many number of controllable states would be there. Okay. So we need to find this z vector, so that zc is the set of is the controllable states and zc bar is the uncontrollable states. So for that we construct a P. Remember that the P matrix has to be invertible. So the first two columns of P are constructed from the two linearly independent columns of QC. So in this case, if you compare, the column 1, 1, 2 is taken from QC and column -2, -2, 6 is also taken from QC. So we have our two linearly independent columns. Now coming to the third column, we need to choose the third column such that the third column is linearly independent from the second two column, and it should be ensured that P is invertible. Okay. I have chosen my third column to be 101 in this case. I suggest that you please verify once if this P is invertible or not. So now once we have this invertible P, I represent the state vector z in terms of x using P as P z to be equal to P inverse x. With this choice, the state space representation that we have in with respect to the state vector z turns out to be in the form of P inverse APZ plus P inverse BU to be equal to z dot and output y to be equal to CPZ plus BU. In this particular example, D is 0, so we will not have this D. On calculation, P inverse AP is revealed to have this particular structure where AC is the block of 0611, A1 is a block of 1.5, then we have a 0 block, and then AC bar is a block with -2, and P inverse B is revealed to be of the structure 1, 0 and 0. So BC has to be of the size, so BC has to be of the size 2 cross 1. Okay. Now CP is in our case 422. So if you notice AC, if you can verify that AC DC pair in this case would be controllable. Also you can notice that the eigenvalue of AC bar is going to be -2, and uh, it satisfies the criteria that all eigenvalues of the uncontrollable part should have negative real part. Okay, so what we have here is AC/DC is controllable, and the real of eigenvalue of AC bar for all eigenvalues, in this case the only eigenvalue is -2, is less than 0. Since these two are satisfied, I mean after canonical decomposition AC/DC is always controllable. We just have to verify whether the eigenvalues of AC bar is are having negative real parts or not. So in this case, eigenvalue of AC bar have negative real part. So what we have in our hand is a system which is stabilizable. Okay, I suggest that you take up a similar system structure, and instead of the eigenvalues -2, you take up sorry, instead of the entries in the A matrix as -2, you take up A matrix whose entries are 2, 2 and 3. Okay, in the same structure, and verify if the linear term invariant system that you have in hand is a stabilizable system or not. So I'll stop here. Thank you.